So section 4.5 is called the substitution rule, and this is a method that allows us to take integrals of certain functions that we wouldn't have been able to with only using the rules. So over time, and especially in 5B, you'll learn more rules as well in order to take antiderivatives and integrate. But this is one of the first ones. As weird as it might sound, this is one of my favorite sections in the book. I actually really like the substitution rule. I like integration in general, but I like the fact that the substitution rule is kind of like looking at a puzzle in a way. So you will hopefully see what I mean very soon. So here we have a function, f of x equals sine of x squared, and the question is, what is the derivative? So you might say, well, I need to take the derivative of sine, and that is cosine. And I'm using the chain rule, so I'm going to have cosine of x squared, but I don't want to forget that I need to multiply by the derivative of the inside. Derivative of the inside is 2x. So I'm going to have a 2x on the outside. And I could also obviously have it multiplied by 2x, but I'll keep the algebra part in the front. So what this means in terms of the stuff we've been learning in the rest of this chapter is that it tells us that the integral of 2x times the cosine of x squared would, dx, would be equal to, so then the antiderivative of this thing would then be sine of x squared, and then of course there is always that possibility that you have a plus c. But it's a reminder that we can take an antiderivative of something and get back to, in this case, like what we were talking about originally, which was that f of x. So now the idea comes up is, what if you were just given what you see down here? And so you hadn't even thought about the fact of sine x squared. So in order to do problems like this, certain problems, we can use what's called the substitution method. So it literally uses substitution. And basically what we do is we take this integral, like that you see here, and we rewrite it so that instead of having x's, it has another variable. And typically this is called u, so this is often called u substitution. You'll see that term as well. And what it requires us to do is it requires us to look at an integral and say, do I have something, and do I also have the derivative of that something? And if you have something, and you also have the derivative of that something, then the substitution rule may be the method you need to use. So in this problem, what we notice is that we have something, and we have the derivative of that something. Now notice, I'm not worried so much in this moment about the cosine, and I'll show you why in just a second. So the something, not the derivative of the something, but the something becomes our u. So in this case, we would let u be x squared. And then what we would do is we would take the differential of this thing. And so remember, that's basically du dx, which is 2x. And that means that du is 2x dx. Now the reason that I do this is because now what it does is it allows me to change this integral into things that only have u and du instead of x. So my x squared is going to become u. And my 2x along with my dx, this piece right here, is going to become du. So notice, that's just right here. And this part is just right here. And so now we can rewrite what we have so that instead of this integral with x, we have the integral of cosine of u times du. Now, the reason we do that is because we know the antiderivative of cosine of something. We don't know the antiderivative of 2x cosine x squared dx. We don't just have a rule for that having been given in one of the earlier sections. We don't have that. But we do have something for the antiderivative of cosine u du. And And what that is the antiderivative of cosine is sine of u. And so we have that. And we can add c. And then we replace the u with what u is equal to, which is x squared. So notice that we have this. So our answer here is sine of x squared plus c. By talking about it in the first piece, I just wanted you to see that logically this makes sense. When you use the idea of the chain rule, you can see that something else kind of needs to be used in order to take an antiderivative. And you want to be able to see that relationship because that's going to help you pick your u so that you can rewrite your integral. And what's kind of the fun part of integration is over time, once you learn all of the techniques, at some point in time, you're just going to be given integrals and your job will just be to find the integral. And you'll have to think, okay, what are all these things I have in my toolbox? What are all these methods I've learned? And so which one fits the patterns that I see in this problem? So over time, that becomes kind of fun and interesting, I think, personally. So a big question is often how to choose u of x. And I've already mentioned this. You want to pick what part of the integral that you have the derivative of. That is your u. So if you look at this example, we have this piece and we have this piece. And you'll notice that one piece is the derivative of the other piece, not the whole thing. So you see x cubed plus x to the fifth. Well, you know the derivative of that is 5 times that thing to the fourth power times the derivative of the inside. So we're not talking about the whole thing to the fifth. But we do know that this piece specifically right here has a derivative that is this piece specifically right here. And because of differentials, we can also replace this piece. And so you can see that we're only going to be left with something to the fifth. And we know the antiderivative of something to the fifth because that's one of the rules we have for integration. So I'm going to let my u equal x cubed plus x. And then typically when we write the differential, we don't do it in 2 steps. We don't write du dx and then write 3x squared plus 1. We would write du equals 3x squared plus 1 times dx. Because we're always looking to replace that whole thing, 3x squared plus 1 times dx, with du. So having that, all the x's on that side is going to, just make our lives a little bit easier. So just go ahead and do that. So we have 3x squared plus 1 dx. We've already learned that that is going to be our du. And that this piece right here that we've already called, set up, is our u. So then, of course, the big thing is rewriting this integral. And one thing that students forget is, like a common mistake, students would say, okay, so we have u du. But don't forget, we did not replace this fifth. That's not part of u or du. So we have u to the fifth du. These are definite integrals here. I'm not evaluating them. We'll do some of those, though, soon. So now I'm going to take my antiderivative. I'm going to add 1 to the exponent. I'm going to divide by that thing. And then I'm going to add c. And then I'm going to replace what I had for u, which is x cubed plus x. And then that's to the 6th plus c. And don't forget, as always, that you are welcome to, take a look at what you got. If you take the derivative of that, does that come back to what you have in your integral? And you can see that you'd use the chain rule and you would do it and you would get what you have in that integral. So there you go. All right, let's do the next one on the page here. So we have this piece and then we have this piece. So notice there's a little more happening here. Then, we have our dx as well. But you might say, well, I don't see the derivative of something explicitly, like exactly. And I agree with you. So if you're thinking, well, I have 3x squared plus 7, and that's on the inside of something. And here's a tip. It's very common to have the inside of sines and cosines and tangents, all those trig functions, be your u. It's also typical to have something in a denominator be your u. It's also typical to have something to a high exponent as your u. because you can't have du inside something. That du is sitting on the end of the integral. Anytime you have that piece sitting in an integral, it's always at the end. So it's never going to be inside or raised to an exponent or in a denominator. And so that could never be your u. So when we have 3x squared plus 7, we might think, okay, well, seems like a good idea for my u. So we'll try it. And yes, sometimes with integration, you just gotta try. And if it doesn't work, then you're gonna try something else. But that's kind of part of problem solving, or it is part of problem solving. So our differential here is going to be 6x dx. And you might say, well, I don't have 6x dx. I have x dx. So you might be saying, I have x dx. Sure. Notice the only difference with what you have in your integral and what you see for your du here is the 6. But the 6 is just a constant. And what we know about constants is they can come outside of an integral, so they can be moved around. So one thing you can do, and different instructors do talk about this differently, you might see something slightly different in another book, just so you know, is I can divide both sides by 6. And so now I have x dx. That's 1/6 du. And I have u being 3x squared plus 7. So now if I change to my red, just as a reminder, I'm going to replace x and dx with a 1/6 du. And then I'm going to replace that 3x squared plus 7 with u. But notice I'm still going to have my secant squared. And don't be too worried about that. We know the antiderivative of secant squared. We've done that in the past. So the way I'm going to write this is I'm going to have my secant squared, and then inside I'm going to have u, and then I'll have my 1/6 du. If you want to have the 1/6 inside, it's not a problem. Bring it inside. But I can also leave it outside because it's just a constant. So I can pull it outside if I want. So now we just have to integrate. So I'm going to have 1/6. My antiderivative of secant squared u is, as we've already learned, it's going to be tan of u, okay, plus c. And then I have 1/6 tan of 3x squared plus 7, and then plus c. And sometimes students have questions about, well, like, why doesn't the 1/6 get multiplied by the c? The thing is, it doesn't matter because at the end of the day, it is still just a constant, and multiplying it by a constant is still just a constant. So it doesn't actually affect the answer in that way. Okay, so looking at the next problem, and again, I'm kind of doing, all the different types here. You have a fraction. And if it is going to be the substitution rule, obviously you first want to look, you don't have just any straight up answer to this, like using the regular rules that you have. Like I mentioned earlier, it's very common for the denominator to have an aspect of u. So it could be the whole denominator, but we notice if I make the whole denominator u, which is the square root of 1 minus x squared, its derivative is going to be a very complicated thing. So, and I don't have that thing. So I might want to only take a piece of things. So notice if I make 1 minus x squared my u, then my du is going to be a negative 2x dx. And then if I solve that, I'm going to have a negative 1/2 du. And so I'm doing that because I have x dx here. So I want to replace x times dx with something. So that's why, again, I'm getting rid of that constant, or it's not gone, just moving it to the other side, so that this tells me that this is going to be a negative 1/2 du. And then this piece right here is going to be u. And then that allows me to rewrite everything with a u, except of course, I'm still going to have that square root. That square root's not gone. So I'll write one line here and then I'll move down. So I'm going to have the integral. The numerator is just going to be a 1. Sometimes you might see the du up there. I'm going to put it over on the side here, but it's no different. I'm going to have the negative 1/2, and then I have the square root of u. Reason we can, we like this and we can do this is because this allows us to rewrite so that we have, of course, the integral of u to the negative 1/2 du. And now we can use the rules that we've learned prior. Very common thing in mathematics is breaking down a problem until it is something that you've seen before, and then using that method that you've seen before. So taking the antiderivative of u to the 1/2, you would say it's u to the, add 1, and then divide by that thing. So we have this, and then I'm going to have, it looks like a negative, and then I can replace my u, which is 1 minus x squared, and plus c. Now, if you write it to the 1/2, that's fine. I mean, I'm not worried about that. You want to do that, no problem. And so now we have our answer. And of course, you could take the derivative of that thing, and you'll come back to that antiderivative that you have before. So, great. Okay, and then let's look at this one here. So one thing that I want you to notice is this is a very basic use of the substitution rule, and if you practice something like this enough, you don't have to use the substitution rule. You can just understand that it's true. Because the cosine is not just an x inside, really the substitution rule is needed, because if you were to think about what's going to create cosine of 5x, it's going to, a chain rule is going to be necessary. And so if we let u equal the inside, very, very common, we'll just have du equals 5 dx, or that dx is 1/5 du. So I would rewrite this as a 1/5 on my outside, and then it's just cosine u times du. And so the only difference, notice, I mean, we're not really replacing that much, except for the inside is now u, and we have a 1/5 on the outside. But we take the antiderivative of cosine, and we just get sine and of u. And then if we, just think about my spacing here, if we just replace the u with the 5x, you can see that we get this. And the reason that I want to do that problem is because this is a rule that we have, which basically just says the rule that for the problem I just gave you, which is that the antiderivative of cosine of a times x, where a is just some real number, is just 1/a times sine of ax. Like, you don't have to do a ton of work. You don't have to use the substitution rule if you can get to the point you can understand that. For the other ones, using the substitution rule is important and needed to show that, but I wouldn't require that on cosine of something or sine of something where the inside is just a constant times a variable. And so notice it also says the other trigonometric functions also follow this idea. So the key thing is, if inside your trig function is just 5x, 3x, pi x, the antiderivative is a lot simpler than you might think, simply because of the idea of a basic substitution rule.